Okay, so in section 5.3, it talked about three collision types, and I just wanted to run through this quickly before I do an example. There are three collision types. There's elastic, inelastic, and completely inelastic. Completely inelastic is sometimes called perfectly inelastic, just so you know. So if you run across those words. Elastic is probably the more complicated one, so let's start with inelastic. Inelastic is just your basic conservation of momentum. Sort of nothing special happens. The two objects hit, they kind of bounce off in whatever directions they bounce off. It's sort of the normal one. In many ways, you could think that's our average or our starting point. Then there are some special cases from there. So completely inelastic is if the two objects hit, they collide with each other and then they stick together and move off as one object. If they move off as one object, as we saw in the note, v1 primed equals v2 primed. If that's true, those two things are the same. We can factor that out. Okay, so there's no change to this left-hand side, but on this right-hand side, we could take out the v primed and say that it's m1 plus m2, and then just call this v primed. It could be either v1 primed or v2 primed because they're the same thing. So when we do completely inelastic, if the two objects hit and stick together and then move off as one, we're seeing something like this. So really it's the same equation, but sometimes you'll see it written like this. The most interesting one, and maybe the more complicated one, is the elastic type, so the first type. In all three collisions, momentum is conserved. Remember, this is always, remember, conservation momentum is that if-then statement, as long as, let's write it here, if there's no external force. So as long as that condition is met, then this is true, P equals P primed. Okay, so momentum is conserved in all three types. There's a little special case here, but in the elastic type, if we're told it's an elastic collision, we have to be told that, but as long as we know it's an elastic collision, then we also know kinetic energy is also conserved. Just note, this is not the full conservation of energy. There's no MGHs, there's no half kx squareds, anything like that, right? This is just kinetic energy. So the combined kinetic energy before the collision is equal to the combined kinetic energy after the collision. I will always write it this way. Something that a lot of people notice right away is, hey, can I cancel out the halves? Absolutely. So you could write it like this. Oops, there should be a 2 there. M1 V2 squared equals, and then M1 V1 prime squared plus M2 V2 prime squared. So you could just write it like this. I'm always going to write it with the halves just so that it kind of reminds people that it's kinetic energy. We're not, if I write it like this, sometimes people get confused between those two. This is not conservation of momentum. This one over here is conservation of momentum. This is conservation of kinetic energy. It is only for this elastic collision type. Okay, so then if we move on to our example that I wanted to do was page 251, number 11. And I just wanted to run through that quickly just so we can see an elastic collision type. Okay, so we're going to use both. Anytime it's a conservation of momentum question, I'm always going to start with conservation of momentum. But then I'm going to ask myself, is it an elastic collision? Am I told that in the question? If I am, that opens up a second equation for me. And I know what you're thinking. At least hopefully you're thinking this. If there's two equations, that means I can have two unknowns. Of course, that's why this is like the most common test question probably. It just makes it a little bit more work. And as teachers, of course, we like those harder questions. So in this question, what we've got is, this is page 251, number 11. We've got a proton traveling with an initial speed of 815 meters per second. It's going to collide head-on with a stationary proton. So the stationary proton is over here. This guy's going to come zooming in and hit it. We're told it's an elastic collision. And we're looking for velocity of each proton after the collision. Okay, so we're looking for what is V1 primed. So after the collision, what is V2 primed? Again, after the collision. We can go ahead, sub numbers in here. I would use conservation momentum to begin with. Something to remember here is, let's write it here, M1 is equal to M2. This is not always the case. Okay, I would say most often this is not the case, but in this question, they're both protons. What that means is M1 and M2 are the same. We can actually cancel those out. We also know V2 is 0. That whole thing is gone. So what we're left with then is just V1 equals V1 primed plus V2 primed. We know V1, let's say this direction is our positive direction. V1, 815 meters per second equals V1 prime plus V2 primed. Now we could take some guessing here. We might suspect that if this guy hits this guy, maybe this guy comes to rest, this guy moves off, or maybe this guy bounces backwards and this guy moves forwards. We could take some guesses, but we don't need to take any guesses. We're going to work it out. Okay, so there's one equation. I'm stuck. I've got two unknowns. But as we mentioned, two equations, two unknowns, we can solve this thing. Okay, so like we said earlier, first thing I'm going to do is get rid of the halves. You can leave them in, but we can remove them immediately. The other thing I'm going to do is, again, cancel those masses. Again, because m1 is equal to m2. So if I clean this up a little, v1 squared, this guy is also 0. Remember, v2 here is 0. Okay, so that whole thing gone. v1 prime squared, v2 prime squared. Again, I can sub in that same number, that 815, that's squared, and v1 prime squared plus v2 primed squared. And there's equation 2. What I've got out of this is two equations. I'm going to solve for one of them, so maybe solve here and sub in over here. You can try to solve for one of these, but as soon as you start taking square roots, that's difficult to sub in over here. It's more work. So I'm going to solve for this guy. I'm going to say v1 primed equals, let's say 815 minus, we'll bring that v2 primed over here. Okay, so there's actually my, I guess my equation 1. I'm going to sub this one, not that one, but this one in here. Sub 1 in 2. What we're going to do then is that guy's going to go right here. So I'm going to have 815 squared. V1 primed is now 815 minus V2 primed. Again, V1 primed is squared, so this whole thing is squared, plus V2 primed squared. Now it's just some math. I'm down to a single variable. We can solve this thing. I'll leave this as 815 squared for now. This thing is going to be 815 squared minus, let's see, 2, so this would be 1630 V2 primed, and then this would be plus V2 primed squared. That's this term, and then I still have a V2 primed squared out here. So I actually have two V2 prime squareds. This 815, something I could do here is I could bring, either way, I could bring this over here or bring this over here. Either way, those guys are actually going to cancel. Okay, so I'm going to say it this way. I'm going to bring this guy over here. Let's write it 815 squared minus 815 squared. On this side, I've got 2 V2 prime squareds and minus 1630 V2 primed. Okay, so this guy is coming over here. Those guys are going to cancel. Those two guys combined give me this term. This minus 1630 V2 primed is still here. Now what I can do is bring 1630 over here. We can divide both sides by 2. We're going to get 815 V2 primed equals V2 primed squared. Now, something I notice here is I can divide both sides by V2 primed. When I do that, I'm actually getting rid of one of my answers. So just keep in mind, this thing's really a quadratic. We could use the quadratic equation. What we know, though, is if this is 0 and this is 0, this equation does work. Okay, so the one root that I'm kind of eliminating when I divide both sides by V2 primed is that root. The other answer, then, is this answer. 815 meters per second. Okay, so there's my two answers. This answer is the no collision answer. Okay, so if, collision, my spelling's not so good. That's an S. What this is saying here is if this guy missed, so if he was down here and he was flying along like this, it could be that this guy just keeps going. Or this guy, remains at rest and V1 just keeps going. So that's the no collision answer. That's not the answer that I want. It's this answer. This is the collision. So if there is a collision, what's going to happen is this guy is going to move off at 815. We can then sub back to figure out. So sub into 1. And we could see V1 primed is 815 minus 815. V1 primed is 0. Is that just on the screen, just barely? what we're seeing then is, this is my combination. So this is kind of my rejected case. It's this set. What happens is this guy here hits, stops, that's that one. This guy here then moves off with the full velocity.